Welcome to Chapter 2, Biology 181. This is Dr. Patterson. We're going to tackle chemical context of life. I know you signed up for biology. Some of you out there are cringing at the thought of chemistry, but that's okay. We've got to do some chemistry in order to do the biology that we need to do. So let's just do some basic review. We're going to talk about things like atoms and elements and matter and compounds and solutions. So let's harken back. Let's go back to the three states of matter. We've got solids, liquids, and gases. You know that. You learned that way back when. Remember that organisms are composed of matter, and that matter is anything that takes up space and has mass. Elements versus compounds. So matter, though that stuff that takes up space and has mass, is composed of elements. Okay, an element is a substance that can't be broken down to other chemical or to other substances by normal chemical means. A compound is different than an element. A compound is when I put two or more elements together in a fixed ratio. Okay, sugar is glucose is C6H12O6. It's 6 carbons, 12 hydrogens, 6 oxygens. That's a compound. Compounds have characteristics different than those elements. So sugar, the compound, has a very different set of characteristics than if I just take carbon or I just take if I just take hydrogen or if I just take oxygen. So very different. We have some what are called the essential elements of life. So about 25 of those of the 92 elements on a standard periodic table are essential to life. The big four are carbon, hydrogen, oxygen, and nitrogen. They're going to make up about 96% of living matter. The remaining, or most of the remaining, not all of it, but most of the remaining 4% is made up of calcium, phosphorus, potassium, and sulfur. And then the last little bit are called trace elements. Those are the ones that an organism absolutely requires, but in very minute, very tiny little quantities. Okay, so each element, I've got this thing, an element. I've got a carbon, I've got a hydrogen, I've got an oxygen. They are made up of atoms. Each element is a unique atom. And sometimes those words get interchanged, and I think I do it even as well. So elements consist of unique atoms. That atom is, excuse me, the smallest unit of matter that still has properties of the element. Can I break down an atom smaller? Absolutely. We'll talk about subatomic particles in a minute. However, we consider the smallest unit of matter that has the properties of the element to be an atom, the same way that we consider the cell to be the smallest functional and structural unit of life. So, again, we're going to do the whiteboard thing, so pause, take notes to yourself, do a little self-check here. I'm going to count to 5. You're going to pause your video. I'm going to give a little break at 5 count, and then I'll keep moving. Okay, so an element cannot be made smaller by normal chemical means. An element is made up of atoms, and atoms are the smallest units of an element that still have the characteristics of that element. And a compound is made up of 2 or more elements. The big four are carbon, hydrogen, oxygen, and nitrogen. Okay, subatomic particles. Remember I said we could break down atoms further? Well, we can. We can break them down into subatomic particles. So we have 3 that we're going to talk about that are relative to what we need to know. And those are protons, neutrons, and electrons. You need to know those. You need to know that protons are positively charged. You need to know that neutrons are neutral. They have no charge. And you need to know that electrons are negatively charged. So protons are positive, neutrons are neutral with no charge, and electrons have a negative charge. We're going to talk about the fact that those protons and those neutrons exist physically in a space called the atomic nucleus. Okay, so we find them in what's called the nucleus. The electrons are not in the nucleus. They're not permitted there. They actually rotate and move around that nucleus in a cloud. Those clouds are called electron shells, electron orbits, or clouds. And we talk about when we measure the mass or we measure the weight, we measure the mass of elements and atoms, we talk about neutron mass and proton mass. And the fact that they are almost identical, they're very equal to one another in a stable element, and they are measured in a unit called the Daltons. Okay, so here are some base definitions. Atomic number, mass number, atomic mass, and atomic weight. You need to know what each of those is. You need to be able to apply those to a given element, and that's one of the things we're about to practice. So the atomic number of protons in the nucleus. The mass number is the sum of the protons plus the neutrons that are in the nucleus. So we'll look at an example for certain, but it's the number of protons and the number of neutrons equals the mass number. If you are given the mass number and the atomic number, you can find the number of neutrons through subtraction. Mass number minus atomic number will give you the number of neutrons. Atomic mass is the atom's total mass, and it's pretty close to the mass number. It's approximated by the mass number. And then atomic weight is an average of all of the naturally occurring isotopes of an atom. And we'll talk about isotopes in a little bit, but basically it's the same number of protons, different number of neutrons, but we'll get to isotopes. So here's just part of a periodic table. We're going to put some of those definitions to work. I blew up the portion with the iron, so down below. So up top is a portion of the periodic table, and then I took that explanatory portion and blew it up. So the atomic mass is up there in the upper left, the atomic number in the upper right. So remember what we said. We said that atomic number was the number of protons in the nucleus, okay? We said that the atomic mass is the atom's total mass, and it's pretty close to the mass number. So we said the mass number was the protons plus neutrons. So I would look at that and I would say, it doesn't tell me exactly, but I'm pretty confident the mass number for this element is going to be 55. Okay? And then the chemical symbol, which are the two letters, the capital F and the lowercase e. The name is iron. Electron configuration will help you a little bit, or makes more sense to you if you've had chemistry before. And we're not really going to use oxidation states. Something they'll use much more in chemistry, something you'll use in biochem, but not really something we're going to use here. So we're going to put these definitions to work, and you're going to find helium. So I've blown up, I've chopped up, I've cropped the chart. I've left your key in the bottom, and you're going to find helium. And then what you're going to do is you're going to answer some questions. So you found the helium, there it is on the right, and you're going to say, how many protons does helium have? So you need those initial definitions that we talked about, right? So number of protons. Well, I know that the atomic number is the number of protons, so I'm going to find the atomic number for helium. Okay, how many neutrons? Well, I know that the number of neutrons can be found if I know the number of protons and if I know the mass number. Okay, well, the number of protons is the same as the atomic number. The mass number is very similar to the atomic mass, and then I have to do some basic math. And then your last question is how many electrons? And this isn't something we've touched on yet, so let's do that right here. Electrons typically will be an equal number to the protons, because when we talk about these elements on the periodic table, they are stable and they are neutral in charge. They are not positively charged or negatively charged. They are not in an ionic form. So if I know the number of protons, I know the number of electrons. All right, so give yourself a second, fill those in, pause if you need to, otherwise answers are coming right now. Okay, so there they are. Atomic number equals the number of protons. Mass number minus atomic number, I'm sorry, atomic mass, because it's very close to the mass number, minus the atomic number will give you neutrons. And how many electrons? Well, electrons are equal to protons, and therefore your answers are 2, 2, and 2. Not all elements do that. I chose helium very specifically because it's a really easy one for us to use as an example. Go ahead and pause your video. Figure these out for hydrogen and for chlorine, and then when you unpause, we'll go ahead and have the answers for you. Okay, so those are our answers. The really interesting thing that frequently will give students a little bit of pause is the fact that there are no neutrons in hydrogen. Hydrogen is very, very tiny. It's essentially a proton inside a nucleus and one electron spinning around, orbiting around it. So that's one that'll trip students up. And then the other part is they sometimes get hung up on 35 minus 17. Just because in all of the other examples we've done, the protons have been equal to the neutrons, it sometimes is tricky for students to recognize that that doesn't have to be the case, that protons are equal to electrons, but neutrons can be a different story. As I promised, we'll talk about isotopes. So isotopes are one element. So I have two atoms of one element. So I have a single element and I have two of them, but they have different neutrons. So in the case, if we go back a slide and we look at the chlorine, we can see that there were 18 neutrons there in the stable. But maybe I have another version of chlorine in which there are 19 neutrons in the nucleus, or there are 20 neutrons in the nucleus. Those are called isotopes. You may have even heard of specifically of radioactive isotopes. Radioactive isotopes are those that have spontaneous decay. So essentially that neutron it's like cramming too many people. It's clowns in a clown car. There's too many stuffed in there. They're bumping around, moving off of one another until they reach enough energy mass to escape the nucleus. And that's the radioactive decay. So they give off these little particles of energy. Why is that interesting to us in biology? You've heard of a lot of this. So we use those radioactive isotopes because we know the rate at which they decay. We can retrospectively work backwards to determine the age of fossils. We use them in metabolic processes. We use them in, we use them in dyes and stains for tracing how certain chemicals or certain metabolites move through the body. We also use it as an imaging aid. We can use radioactive isotopes to measure, or to visualize rather, not measure, but to visualize urine flow through the urinary tract, from the kidneys down the ureter into the urinary bladder. We can use radioactive isotopes to see if there are regions within the thyroid gland that are more reactive or dividing cells faster than other areas. Okay, that's going to move us into these electrons. So we need to talk about electrons, because electrons are, while they're teeny tiny and they don't have a lot of mass to them, they're super duper important to everything else we're going to talk about. So before we jump into those, let's grab some basic definitions. We need to talk about energy and potential energy. So energy is that capacity to cause change. Potential energy, potential energy is the energy that matter has because of its location or structure. Because of the way it's put together, it has a certain amount of energy. There's energy held within the bonds between those elements and between those atoms. Or maybe potential energy exists because of where something is physically located. Okay, we'll talk about that in in the next slide, actually. Electrons of an atom have different amounts of potential energy depending upon which orbit they're in. So thus far we haven't really talked about there being multiple orbits, but we need to. And we need to talk about the fact that energy varies between electron shells. Okay, so let's look at this visual. So there's the atomic nucleus, that gray circle, and in it, that's where our protons and our neutrons are. And then our electrons will be arranged in shells outside of that nucleus, okay? And the first shell, the lowest energy shell, that one only holds 2 electrons. And then we have a second shell, a higher energy level. It has more energy. So the further away from the nucleus you are, the more energy you have. It's like, or more potential energy you have. It's like being on steps, okay, or on a ladder. The higher up the steps or the higher up the ladder you go, the more potential energy you have, okay? So third energy shell in your visual is going to have the most energy, okay? So as I move up or away from the nucleus, as I move out in the shells, I'm going to absorb energy, and therefore I'll have more potential energy. As I lose energy or I drop back and I fall into shells closer to the nucleus, then I have less energy. How an atom behaves chemically is really determined by how many electrons there are and which shells they're in. And the periodic table shows us that. I showed you that we had that electron distribution. You can also do it just by knowing how many electrons there are and knowing that certain shells will only hold a certain number of electrons. So like I said, I'm going to go back a slide. Like I said here, that first shell is only going to hold 2. My second shell is going to hold 8. My third shell is going to hold 8. That's a really abbreviated, simplistic version of electron shells. If they fascinate you, chemistry is the place for you to be. But I'm going to teach you just enough to do what we need to do in biology. So here's your electron shell definition. The outermost shell that has electrons in it is called a valence shell. The electrons in that shell are called valence electrons. If the outer shell is completely full, okay, then it's considered inert, meaning it's chemically stable. It doesn't want to give up any electrons. It doesn't want to lose any electrons. Its shell is full. It's happy. It's content. Okay. Orbitals are those shells, so we call those shells orbitals, and they're three-dimensional. They're not flat, they're not a single ring like they look like when we draw them. They're three-dimensional around that nucleus. And each electron shell has a specific number of orbitals. Each orbital holds 2 electrons, so we're going to call those s orbitals and p orbitals. I'm not going to make you regurgitate and memorize that and spit back the S and P's to me. I'm just going to ensure that you know that s orbitals hold 2 electrons. P orbitals are subdivided into suborbitals of x, y, and z. Each of those hold 2, so in total the p orbital will hold 6 electrons. That's how we got to the point of me saying that the second shell will hold 8 electrons. The s will hold 2, the x, y, and z each hold 2, so the overall combination of x, y, z, which is called p, that holds 6, and therefore we get 8. I'm talking a lot of words and I haven't given you a visual yet, so let me do that. Okay, so I've got a nucleus. I typically do the electron dot drawing that's up at the very top of this image. So my gray nucleus, my first shell, has 2 electrons in it. It's full. My next shell, my second shell, is made up of an s and 3 p orbitals, the x, y, and z. And what I have there are 2, 4, 6, 8. The little yellow dots are the electrons, so I have 8 electrons in that valence shell. All totaled, all together, this is neon with 10 electrons. How did I know it was neon other than it said it right there? Well, if I look at this, I see 10 electrons. Remember that I'm going to have the same number of electrons that I have of protons. And if I look at a periodic table, neon has an atomic number of 10. Okay. So, whiteboard. Go ahead and do this. pause your video to give yourself time. I'm going to count to 5 and then I'll reveal the answers to you. Okay, the chemical symbol for nitrogen is a capital N. Yes, it needs to be capitalized. Number of protons, 7. I know that because the atomic number is 7. How many electrons? 7. I know that because the number of protons is equal to the number of electrons. And how many neutrons? Your answer is 7. I'm going to subtract the atomic number from the mass number. And then drawing the electron distribution diagram, I have the center nucleus where the protons and the neutrons are going to live, and then I need to distribute out 7 electrons. So I start with my first shell, it'll hold 2. So I put 2 in my first shell, 7 minus 2 is 5, so I have 5 left over. There are plenty of spaces in the second shell for 5 electrons, so I draw 1, 2, 3, 4, 5. See that? Okay. Why electrons are so important to us is because they are the subatomic particle that creates the chemical bonds. We don't get molecules and compounds without electrons. They are the attractive forces between elements. And so any atom with an incomplete valence shell can either share its electrons, right? Or it can actually even transfer valence electrons. It can steal electrons from another, or it can give them up and let somebody else have them. These interactions and these attraction happens because atoms are so close together. And when we have these changes in electrons, either sharing them or transferring them, we call those things chemical bonds. So we're going to talk about some different chemical bonds. We're going to talk about covalent, we're going to talk about ionic, we're going to talk about hydrogen bonds, but we're going to start with covalent. Covalent bonds are pretty cool. They are the strongest of all the chemical bonds that you and I will talk about. They happen whenever 2 atoms share valence electrons. So somebody has, 1 in their outer shell, they've got an opening, and somebody else has just 1 in their shell, and then they're going to share. And you're going to see that visual in just a second. But what ends up happening is because they're sharing, they both get to count them. Okay? So let's just look. So I have 2 hydrogen atoms here, right? And what ends up happening is they end up sharing, they each have 1 electron, and they end up sharing that electron. So what that means is they now both have 2 electrons. They really only have their original one plus their share time with the other, but that's enough for them to have a stable, full valence shell. And that makes those atoms very, very happy. Okay, so we'll see that quite frequently, that hydrogen will hang out in a bond with hydrogen. Bonds, so just in general, we talk about single bonds, double bonds, triple bonds. So molecules that have 2 or more atoms and they're held together by covalent bonds, that's your definition for molecule. We can have a single bond, that's 1 pair of valence electrons that are shared. Or we can have a double bond where they share 2 pairs of valence electrons, and we write that with a double line. Or what do you think a triple covalent bond is? Exactly. It's when we have 3 pairs of valence electrons being shared between 2 or more atoms. There's lots of different ways to write this, and like I said, I'm just going to give you enough chemistry to get you through the biology we need to do. Chemistry is in itself, as you know, an entire course, and I'm not going to do it any bit of justice in what I'm doing, but I'm giving you just enough to get by. So a structural formula will tell me that I have 2 hydrogens, and do you see that single line there? That tells me I have a single bond between there. If that were a double line, like an equal sign, which can't happen because of the number of electrons, but if I did have that, it would be a double bond. That's different than a molecular formula. In a molecular formula, they just tell me how much of each element is present. So in this case, I know that I have 2 hydrogens. It doesn't in any way show me or indicate to me the bond structure, whether it's single, or a double or anything else. It just tells me who's present and in what quantity. So here's some different ways that we talk about molecules. There's electron distribution diagram. There's a Lewis dot where they just use dots instead of the circles, and then a space filling model. I believe this is in, or some version of this will be in your textbook if you want to look at it more closely. Okay, so we talked about valence. We talked about a valence shell. We talked about valence electrons, but what is actually valence? So remember that I said that covalent bonds can form between atoms, either of the same element or of different elements, and that they're going to share their electrons. A compound is going to happen when I have two or more different elements. Okay, so I can have a molecule of water, right? H2O, 2 hydrogens, 1 oxygen, and at the same time, I can have a compound. I can have H2O because I have different elements. Now, here's a word that's tricky. We talked about a valence shell. That was the outermost shell of an atom that had an electron in it. And we said that the electrons in that shell are called valence electrons. Now we have to talk about the openings in that shell. So if I'm in the 2 orbital, the 2p orbital, and I have 5 open spaces, meaning I only have 3 electrons in that shell. I have 5 open spaces. What that means is that atom has a valence of 5. It's the number of open spaces that can either that can share an electron or acquire an electron from somewhere else. Okay, I'm going to pause here. We're just at 26 minutes, and I'll do a second video picking up with electronegativity and then finishing off the chapter.